The title of today's lecture is Reduction of a Simple Distributed Loading. As such, we are going to cover certain activities based on our objectives. Our objective is to be able to determine an equivalent force for a distributed load. We would include in our activities a reading quiz, applications, equivalent force, concept quiz, group problem solving, and an attention quiz. So let's start with a reading quiz. The resultant force due to a distributed load is equivalent to the blank under the distributed loading curve. W equals W sub X. So let's think about that. The correct answer is the volume. We're not dealing with the volume loading when we are in a two-dimensional XY coordinate. And the arc length, we don't do that. The centroid, we don't do that. We actually replace the area under the distributed load by an equivalent area to be able to simplify the procedure and simplify our calculations. The line of action of the distributed load's equivalent force passes through the blank of the distributed load. That's number 2. It actually is going to pass through the centroid of the distributed load. Let's start by taking a look at some of the applications. As you can see here, this is a storage facility in which the it's like a pallet of a 2x4 or some other kind of material there, put on top of a simple cantilever beam. One side it is connected to a point A, and the other side it is free. And in order to simplify our calculations, we would like to pretty much replace a W sub O, which is a uniformly distributed load, by an equivalent concentrated load. So we need to do that because we need to often analyze the effect of such a load on the beam itself or on anything that supports such a load. Another application, again, which is pretty popular in Florida, is the uniform wind pressure that is acting on the building. In this case, there is a triangular sign shown in light brown, and you would like to calculate the wind pressure, making sure it can withstand a certain pressure associated with high velocity wind. So in order to be able to design the joint between the sign and the pole, or even to be able to determine what should be the joint at point O, we need to calculate the resultant forces. So what is a distributed loading condition? A distributed loading condition is a surface area of a body that is subjected to more than one concentrated load. This could be, again, as shown in some of the examples, such a force could be caused in most cases by the wind and by fluids, the gravity, the weight of the items on the body's surface. So these are some of the typical conditions. So what's the most common distributed pressure loading? Again, we would like to consider that. This type of loading could also be simply the pressure of soil or pressure of earth in case we design retaining walls and other similar cases. So we will analyze the most common case, and in this case it's a uniform load along one axis of a flat rectangular body. It's pretty much a two-dimensional as shown down here. In this case, W is a function of X, meaning that the distributed load could vary along the x-axis. So it's not going to be, it may or may not be a constant throughout. If it's in the form of like a rectangular load distributed but rectangular type, then we don't need to worry about the variation x. But this pretty much W expressed as a function of W sub x, and that what it really means is that it can vary along the x-axis. The magnitude of W could vary along the x-axis. So, for example, here it could be 500 pounds, and down here it could go down to 100 pounds with the variation shape as shown by this diagram. So we would consider an element of length d sub x. This element is much smaller. What we use in this case is we use integral. We integrate that over the entire load. As such, we should be able to calculate F sub r, a resultant force. The net force of the beam is given by the integral over L, over the length L in the x direction, W sub x d sub x. Again, don't be scared of that. Just we integrate that over that entire length of x. The small d sub x is the very small element of length d sub x, and A is the area under the loading curve W sub x. Okay, so we are going to also have a moment about point O as a result of df, a small portion, that small d sub f times x, and that x could be very small. It could be much larger than d sub x. So the total moment about point O is given as, again, the integral of that multiplied by x, which is the length from the point O. So assuming that F sub r act at x bar, it will produce the moment about point O as such, x bar multiplied by F sub r, and again we pretty much need to integrate over the entire length of L x bar, so we take the x out since it's a number, it's a constant number, then this should be an integral, okay? L over entire length of LW sub x dx. So we integrate over that, and then we would, comparing the last two equations, we would get x bar as such, and you will learn about this later more in detail, but F sub r acting through a point C, which is the geometric center of the area, or what we call the centroid of the area under the loading curve. We would discuss centroid later on in the course. Let's take a look at some examples here, because our discussion would not be complete without providing you some examples. So for now, until you learn about centroids later, we would look at some of these rectangular and triangular loading diagrams. The centroids are well defined. They are shown on the inside back cover of your textbook. If they're not, there are tons of resources available on the internet. You can use those, or simply let me know. I can provide you with some simple diagrams. So again, in this case, a 400-pound foot load could be replaced by 400 times 10. That's 4,000, acting exactly at the center of the beam, which in this case is 5 feet away from the left-hand side or the right hand side of the beam. Triangular load, we simply get the area, calculate the area of this triangle, 600 times 6 divided by 2, or simply 600 times 3, 1800. We would place it at 2/3 from the left-hand side of the distance, 2/3 away from the left-hand side and 1/3 away from right-hand side. The length of the beam is 6 meters, so 2/3 of that would be 4 meters. So it's going to be located right here. Okay. Other examples, again, we can simply do that as I just explained to you. Okay, so what is the location of f sub r? The distance d in this case. This is a very interesting problem because this would be applied 2/3 from here, so this distance would be 2, so it's 3 plus 2, that is 5, right? So the correct answer is D. Next, if F1 is 1 Newton, X1 is 1 meter, F2 is 2 Newton, X2 is 2 meter, what is the location of F sub r and the distance X in this case? The answer is D, or 1.67 meter. Again, as you can see, the F1 is 1 Newton, F2 is 2 Newton, so this is 1, this is 2, and X1 is 1 meter, X2 is 2 meter, okay? And as such, when we do follow the procedures that we just did in pretty much adding them up and find a location in between, again, we need to make sure we also consider that. So it's going to be somewhere a distance between 1 and 2. In this case, it's going to be 1.67, considering the moments. Again, you got to do some simple calculations, calculate the moment with respect to a point, and then try to find an equivalent force that causes the same moment with respect to one of the points on the beam itself. Okay, so let's take a look at another problem solving. This is more complicated. Then we do an attention quiz and we wrap it up. So the loading on the beam is shown. The equivalent force and its location from point A is what we would like to determine. The plan is, again, we in this case we could divide it into three areas. One could be from A to B, and from B to the right side of the beam. We can also divide that into 2 areas. So one would be, there's one triangle here, there is another triangle here, up here, and there is a third one, which is a rectangle, is down there. So we're going to find F sub r and its location for each of these 3 distributed loads. We're going to determine the overall F sub r of 3 points and its location. So for the left triangle loading of 8 kN, we would multiply that by 1.5, right, to get the area of the triangle. The area is 12 kilonewton in this case. Again, this is not really the area, but we are trying to calculate an equivalent load for that is pretty much represent that area. So when I say area, we don't do an area calculations because our units are not the area unit, but we are finding the area under that particular loading curve. In this case, it's a triangle. So x1 would be 2/3 times 3. It's going to be 2 meters from A. And for the top portion, we will do the same thing. It's going to be 1 meter. It's going to be actually 2 meters from here. This is going to be 2. Okay. If I want to only replace the equivalent, the distributed loaded top triangle with a concentrated load, that's how it's going to be. And then for the bottom one, the same thing. For the rectangle, it's going to be right at the center. So now we have 3. For those 3, we take F sub r is going to be 30 kilonewton. And then we take the moment about the point A, as I just discussed for the previous problem. And it's going to be 109 kilonewton meter. Now we're going to replace we're going to find the equivalent. The FR x bar has to be equal to this quantity has to be equal to m sub r a, 109 kilonewton meter. And so we solve for x, and we would locate that 3.4 meter from A. Okay, and attention, quiz. In this case, we would like to find F sub r. What would be F sub r in this case? Again, 12 times 100 divided by 2. Simply, it's going to be 600. Again, I just did a mental calculation. You can grab your calculator and do that, and you would get the same results. X would be then for the same loading condition. We have that, and then now we're going to find X. Again, do a mental calculation, get the moment about one of these forces. Again, this is for the same problem, so don't be scared what the magnitude of F sub r would be. This is simply this one, okay? So after we calculate F sub r, now your F sub r is 600. And that would be actually 4 meter. Okay. That brings me to the end of the lecture. Let learning continue. As always, if you have questions, please feel free to contact me. Thank you.